So for this last part for our lectures, I'm going to lead off with three different examples that are beyond our pay grade to explain what this is. It might make more sense when we talk about molecular orbital theory later, but this is kind of highlighting a limitation of our electron counting formalism. And so we have some fancy kinds of bridging ligands to deal with. And so I'm going to draw all of these out and then we can talk about them because thankfully they're all kind of the same, but they're going to be really weird and confusing. So kind of buckle up and prepare for the weird things that look like these structures. So we can have bridging hydride ligands. We can have bridging carbon ligands. And again, that looks like a Texas carbon, which looks gross. My inner organic chemist does not like drawing that. And we have bridging carbonyl ligands, right? So this is a bridging hydride. A bridging carbon. It would help if I could spell bridge. Bridging carbon. And we have bridging carbonyls. Now, the reason that these are so weird is because right now we cannot worry about oxidation states for these. We can't really worry about the impacts that these have in interpreting what these lines look like because they very much violate what we normally think of when we think of these Lewis structures. But what we can do is we can define these in terms of their electron counts. So all three of these types of ligands, right, all three types are what we call two electron donors, right? So these are two donors, two electron donors that are spread out over three atoms. And again, the specifics of what's happening here is well above our pay grade to try to explain. But we can use this. We will see these in some transition metal complexes. And so it is useful to kind of be able to think about how we approach these and what we can use them for. So the last kind of weird bonding that we will see, so now that we've had all these bridging ligands in our discussion, is trying to understand metal-metal bonds. So in order to get a better look at this, we're going to look at manganese pentacarbonyl, right? So manganese with 5 COs. So if we draw this out, we could draw it out to look like a trigonal bipyramidal system. But I'm going to skip ahead a little bit because we're going to do our electron count. We've seen these, and so we can draw these out already. And so if we're going to try to figure some of this stuff out, we have our manganese, and we look at our periodic table to see that manganese brings with it 7 valence electrons. We have 5 carbonyls. We know that each of those are a 2-electron donor. And so we can see that the manganese complex itself is 17 electrons. It hasn't quite reached our 18 electron guideline that we're looking for. And as it turns out, this manganese pentacarbonyl reacts a lot like a free radical, right? So think kind of like, you know, a methyl radical. So if we had a methyl radical in solution, what would happen? Well, this methyl radical is going to dimerize, meaning we have our manganese, and they are going to react with each other, right? If they each react like a radical, then we have those electrons that can form new chemical bonds. So we have all these CO ligands that are now attached. Right, and this comes from a dimerization. And so the kind of new feature here is that we actually formed a metal-metal bond. So how do we do electron counting when we have a metal-metal bond? Well, what we do is we count for the entire system and then divvy up the electrons, right? So we do the entire system or entire, metal system to determine how many bonds there are between our manganese centers. So I have 2 manganese, therefore I'm hoping that I can get to 36 electrons. And again, there's going to be some weird hand waving that occurs here in order to use our electron counting formalism to determine the number of bonds that we have here. So I know that I have a total of 10 CO ligands. So that means I have a total of 20 electrons from just my COs. I have my 2 manganese, right? And these brought with them each 7 electrons. So I have a total of 14 electrons. So if I'm just looking at the valence electrons that I have around, this looks like I have 34 electrons. So how can I get up to 36, right? Like I said, if we have 2 manganese atoms, right, I want to get to 36 electrons. Well, I can account for the fact that I have a manganese-manganese bond. If I'm drawing if I'm drawing a bond in kind of a Lewis structure, we would say that that's 2 electrons. And this gets us to 36 electrons. Now, I know what some of you are thinking because this is something that every once in a while I still kind of get wrapped up on. We are double counting electrons here, all right? And if it seems like we're double counting electrons, it's because we absolutely are. The reason that we're double counting, right, these electrons here that we're saying is this manganese-manganese bond are 2 of the electrons from the valence shell of these manganese. Where this 2 electrons comes from is it's just the sharing of these electrons between my manganese centers. So the reason I'm double counting them is because they're sharing with each other. And so it's kind of weird, but this is how we can use our 18 electron formalism to determine a kind of bond order for our metal-metal kinds of bonds. The other way you could think of this is that a metal bond acts, or a metal center acts like a 1 electron donor per bond, right? So if that makes it a little bit easier to think about, that also works for electron counting. So we could say that a metal bond is like a 1 electron donor. And I will say that this is per bond, right? So if we have a metal-metal double bond, it acts like a 2 electron donor. If we have a metal-metal triple bond, it acts like a 3 electron donor. And so this is another way you can kind of approach this. Sorry for my kind of janky line there. But we can think of a metal-metal bond kind of like being a 1 electron donor in our systems here, right? So now we have some methods where we can deal with metal-metal bonds, we can deal with bridging ligands, we can deal with haptic ligands, and we can deal with polydentate ligands. These are lots of fancy ligand classes, but really all it comes down to is figuring out how they can be 1 or 2 electron donors and how they impact the oxidation state. Our next class, we're going to do more practice with electron counting. We're going to have a bunch of complexes that we dig into, complexes that have polydentate ligands, complexes that have haptic ligands, complexes with bridging ligands, and complexes with metal-metal bonds. And so you're going to get practice with this. We're going to spend some time making sure we're comfortable with kind of drawing out these inorganic complexes because, again, this is foundational for our quarter. We're going to be doing a lot throughout this quarter in terms of structure. And when we draw them out, we want to be able to quickly identify X and L type ligands and kind of figure out the oxidation state of the metal, because that's going to be extremely important when we get to ligand field theory and when we're talking about bonding. We need those d electron counts. All right. So now we have lots of different ligand types, lots of practice we can dig into in determining our electron counts for our metal complexes.